Thus, we have found the solutions of area differential equation as A of theta and B of theta, but we are interested in the asymptotic values of these solutions. The asymptotic values, asymptote, as you know, the definition is the tangent of the curve at infinity. So we can find the asymptotic values of A of theta and B of theta by following the procedure of finding the tangent of a curve at infinity, which you have done during your degree classes. I'll give you the asymptotic values only. I am not going to show the derivation. You can follow the same procedure for finding the tangent of a curve at infinity to find the asymptotic values of A of theta and Bi of theta on both regimes. This I suppose you may take as an assignment. For the time being, I am not going to show the derivation here. The asymptotic value of A of theta in the limit theta tends to 0, theta much less than 0. Theta, as you know, is 2 mu c by h cross raised to 1 by 3 into x minus x1. When theta is much less than 0, x minus x1 is in fact much less than 0. X minus x1 is much less than 0 or is negative. That means x is smaller than x1. That is possible if and only if the region represented by these arbitrary choices of x is behind the turning point, say x1. That is exactly the region 1. So the asymptotic value of ai of zeta in region 1, that must turn to the oscillatory solution represented by WKB. So this is identical with the WKB oscillatory solution, and the value of this asymptote is found to be alpha by root p sine of 1 by h cross integral x to x1 p dx prime plus pi by 4. Here the integration is from x to x1, that is a positive limit, as x is behind, say, x1. In all these we will be representing positive limits only, though we have taken some negative limits in the limits earlier. So this is the asymptotic value of ai of theta in region 1. Similarly, in region 2, asymptotic value of A of theta, that must turn out to be the exponential WKB solution in region 2. Theta is much greater than 0. That means x much greater than x1. So x, arbitrary choice of x, is, say, somewhere on the right side of x1, the turning point. That is a solution corresponding to region 2, and the value of this asymptote is found to be alpha by 2 root p e raised to minus 1 by h cross integral x1 to x p d x prime. Here also x1 to x is a positive limit because we have region 2, x1 is behind x. So these are the asymptotic values of A of theta on the two regions that represent the values of the curve, values of the same curve at two extremities. Definitely they are related to each other. Then this relationship is in region 1, that is classical region. The wave function that is represented by a sinusoidal oscillation is modified to a decreasing exponential term in the quantum mechanical region or in region 2, with the constant multiplying the sine function in the oscillatory region becoming half of the coefficient of the decreasing exponential term. Similarly, the asymptotic values of Baire function are given here. Bi of theta in the limit theta much less than 0, that is region 1, that should be complementary with the WKB oscillatory solution in region 1, and this value of asymptote is found to be alpha by root p cosine of 1 by h cross integral x to x1 p dx prime plus pi by 4. This is again positive. Here also this is positive. Similarly, the value of Baire function in the regime zeta much greater than 0, that should turn to be identical with the WKB exponential wave function in region 2 in the limit x much greater than 0 is found to be alpha by root p e raised to 1 by h cross integral x1 to x pd x prime. These are the two extreme values of one and the same curve. So they are identically related to each other. This gives us the second connection between the two WKB wave functions. The WKB wave function represented by a cosinusoidal oscillation in the classical region becomes an increasing exponential term with the constant multiplying the increasing exponential exactly the same as that of the constant multiplying the cosinusoidal oscillation. In these expressions, alpha is a constant given by 2 mu c h cross by pi cube raised to 1 by 6. So, the asymptotic values of the two solutions give exactly the connection between the possible WKB solutions in the classical and quantum mechanical, or rather than quantum mechanical, I must tell you non-classical regions. And these are summarized for convenience like this. In classical region, the solution is oscillatory, and the solution can be represented either by a sinusoidal oscillation or using a cosinusoidal oscillation. In the non-classical region, the solution is exponential, and this exponential solution can be an exponential decay or an exponential growth. How these oscillatory counterparts of solutions are related with the exponential counterparts of solution, that is exactly what is known as connection formulae. This connection is like this. The oscillatory solution represented by a sine wave function becomes a decreasing exponential term in the non-classical region, with the constant multiplying the decreasing exponential getting halved, comparing with the constant multiplying the sinusoidal oscillation in region 1. That is the first connection formula. Now the second connection formula. This is the first one. Sinusoidal oscillation get modified, or sinusoidal wave function get modified as decreasing exponential. And keep in mind that in this oscillatory part there is an additional pi by 4 parameter that will be missing in the exponential term. The second connection formula is, or can be stated as, the WKB wave function represented by a cosinusoidal oscillation in the classical region get transformed to an increasing exponential wave function in the non-classical region, with the constant multiplying the increasing exponential exactly the same as the constant multiplying the cosinusoidal oscillatory solution. So this is the connection formula. Keep this in mind. There are 2 points to be kept. Wave function represented by sinusoidal oscillation in the classical region becomes decreasing exponential solution in the non-classical region, with the constant multiplying the decreasing exponential just half of the constant multiplying the sinusoidal oscillation. The wave function represented by a cosine function in the classical region is modified as an increasing exponential wave function in the non-classical region, with the constant multiplying the cosine wave function and the increasing exponential term being exactly equal. So these are the core points that are to be kept in mind as long as the connection formula is concerned. We will be making use of this formula for a few more derivations that are yet to come while we talk about the applications of WKB method within the limit of the demand of our syllabus. However, the overall WKB solution in region 1, I have written it in terms of an exponential parameter with coefficient being I. I didn't represent this in this particular format. So this is to be represented for a comparison. Overall WKB wave function in region 1 is a1 by root p e raised to I by h cross integral x1 to x p dx prime plus b1 by root p e raised to minus I by h cross integral x1 to x p dx prime. That I will have to represent in this particular format. This exponent with I parameter needed to be written in terms of the sine and cosine terms that we will do in the next. For that, we make use of the de Moivre's expansion e raised to I theta equal to cos theta plus I sin theta, where theta being say 1 by h cross integral x1 to x p d x prime. So a1 by root p e raised to minus I by h cross integral x to x1 p d x prime. I will be multiplying and dividing this term by e raised to I pi by 4. E raised to minus I pi by 4 is given here. E raised to I pi by 4 is also given here. And this is done for the second term as well. b1 by root p e raised to I by h cross integral x to x1 p dx prime. E raised to I pi by 4 e raised to minus I pi by 4. This is the WKB wave function that we have taken, which generally we write from x to x1, where x1 is the turning point. As long as region 1 is concerned, x to x1 is positive. It is in that positive manner we have written the asymptotic values of Airy and Bailey functions as well. Now club these terms having this negative power, a1 by root p e raised to minus I is taken as a common term, I into 1 by h cross integral x to x1 p dx prime plus pi by 4 e raised to I pi by 4 plus b1 by root p e raised to I into 1 by h cross integral x to x1 p dx prime plus pi by 4 into e raised to minus I pi by 4. For the sake of convenience, let me label this quantity say theta here also as well as here. Then this is a1 by root p e raised to minus I theta e raised to I pi by 4 plus b1 by root p e raised to I theta e raised to minus I pi by 4. Now we substitute this de Moivre's expansion cos theta plus I sin theta. Here this is e raised to minus I theta, that is cos theta minus I sin theta. Here it is substituted cos theta plus I sin theta. Now there are two terms containing sine and two terms containing cosine. Club them. Sine is taken out. Here what remains is minus I a1 e raised to I pi by 4, and in this term once sin theta is taken out, what remains is I b1 e raised to minus I pi by 4 divided by root p into sin theta. Similarly, cosine term is taken out. What remains here is a1 e raised to I pi by 4 by root p is a common denominator, plus b1 e raised to minus I pi by 4. That is minus IA1 plus IB1 into e raised to minus I pi by 2. I have taken e raised to I pi by 4 outside by root p sin theta, and from this term e raised to minus I pi by 4 is taken outside, so that A1 will have a coefficient e raised to I pi by 2. That is minus I a1 plus b1 I into e raised to minus I pi by 2 is cos pi by 2 minus I sin pi by 2. Cos pi by 2 is 0. Minus I sin pi by 2 is 1. So here we will have minus I. And this term becomes a1 e raised to I pi by 2 is cos pi by 2 plus I sin pi by 2. That is I plus b1 e raised to minus I pi by 4 by root p cos theta. Now this is rearranged as minus I a1 plus b1 I into minus I square, that is plus 1 e raised to I pi by 4 by root p sin of theta is exactly this quantity 1 by h cross integral x to x1 p dx prime plus pi by 4, that is written here. Here also for cosine that is retained. This is another constant. Minus I a1 plus b1 into e raised to I pi by 4 may be taken as a constant.